In the vacuum of deep space, gravity doesn't just pull on matter, it warps the very fabric of physical reality. In physics, a dimension is a rigid, structural limit. It defines the specific directions in which our universe is allowed to extend. Unlike the three spatial directions we navigate daily, the fourth dimension, time, is bound by causality. We cannot move through it with the same freedom we use to walk across a room. This absolute boundary is the core of Albert Einstein's spacetime, where the rules of the universe are written in 4 dimensions. These 4 dimensions dictate the trajectory of every particle, the reach of fundamental forces, and the speed of light itself. The difficulty begins when we try to force these same physical rules onto the abstract world of mathematics. Most students hit a wall in linear algebra because they try to visualize a 4th or 5th mathematical dimension as a physical shape.
To a mathematician, the physical existence of a dimension is irrelevant. They're interested in logical consistency, not material reality. In this context, a dimension is defined simply as an independent variable, a single, distinct direction for a coordinate to move. Mastering this subject requires disconnecting the word dimension from the concept of physical space entirely. The most effective way to conceptualize n-dimensional space is not through geometry, but through a spreadsheet. In mathematics, an n-dimensional space is essentially a dataset with n independent columns. Every individual row in that dataset represents a single coordinate point or vector within that space. Consider a housing dataset. A single row containing 5 different metrics is by definition a 5-dimensional vector. We are tracking square footage, the number of bedrooms, distance to the nearest school, age, and price. These 5 traits act as independent axes. You can change the number of bedrooms without automatically dictating the age of the house. In geometry, moving along one axis while the others stay perfectly still is the definition of perpendicularity. Because these variables can change independently, they are mathematically identical to axes sitting at 90-degree angles. This logic allows us to scale far beyond what we can visualize. A small digital image is actually a massive list of over 4,000 variables, one for the brightness of every pixel. A computer vision algorithm treats this entire image as a single coordinate point. It plots that point inside a 4,096-dimensional space. By translating visual media into coordinates, we enable computers to process the world through pure geometry. How do we calculate distances or intersections in a space we cannot physically see? Mathematicians use algebraic extrapolation, a method of expanding known patterns into unknown dimensions. We start with the geometry we can see, like a simple flat graph. In 2 dimensions, the Pythagorean theorem calculates the distance to a point by squaring and summing 2 variables. Notice the symmetry of the formula. It doesn't matter what the variables represent, it only cares about the pattern. To find a distance in 3D, we simply add a 3rd variable to the same sequence. This mathematical pattern holds even when we step into spaces that cannot exist physically. For a 10-dimensional space, we continue the chain to the 10th variable. The algebra works flawlessly, whether we are calculating the distance between 2 houses in a dataset or 2 stars in the sky. This allows data scientists to perform precise calculations in infinite dimensions without ever needing to see the space they are working in. Even with algebra, we eventually encounter complex topologies, like vector subspaces, that demand a geometric mental model. In formal linear algebra, we often analyze matrix equations with 4 or more unknowns. These equations describe relationships occurring in spaces we cannot perceive, such as a 4D null space. To handle this, we use a 3D shadow, a simplified geometric metaphor that preserves the logic of the higher space. Picture a flat 2-dimensional plane slicing through a standard 3-dimensional room. We treat this room as a stand-in for the full n-dimensional space. The way vectors project onto that plane or intersect at right angles is mathematically identical, whether the room has 3 dimensions or 3,000. Attempting to visualize a 2D plane passing through a 4D hypervolume directly is a cognitive dead end. By scaling the problem down to a 3D shadow, we keep the geometric logic intact without overwhelming our spatial intuition. Navigating the dimensional divide requires a shift in perspective across data, calculation, and visualization. We map raw information to spreadsheets, use algebra to calculate what we cannot see, and use 3D shadows to understand the topology. When we decouple math from physical intuition, the mystical elements of higher dimensions disappear. We are left with a powerful organizational tool designed to track thousands of interacting variables at once. This is how modern neural networks find subtle patterns within million-dimensional datasets that no human observer could ever perceive. Embracing this abstract definition of dimension is what allows us to compute the complexities of a world that far exceeds our three-dimensional vision.